Welcome back everyone for the next session, second session of the first day of this conference. In this session, we have the session chair Lakshita Jindal, who is a PhD student at JNCASR, and she will be first summarizing the housekeeping rules that she's going to follow, and then she will start the session. So over to you, Lakshita.
Thank you, ma'am. So hello everyone, my name is Lakshita. I am chairing the second session for this conference. So I'll quickly go through the rules. So each speaker will get 15 minutes in total, 12 minutes for presentation and 3 minutes for question and answers. After 10 minutes, the speaker will be reminded that 2 more minutes are left. And also the questions will be taken at the end of the presentation. So no questions will be taken in between, and you can raise hands and the questions will be taken at the end of the talk. So yeah, so our first speaker for this session is Dr. Sanjay Kumar from Banaras Hindu University. Yes, so you can start.
Yeah, so is my presentation is visible and I am audible?
Yes,
yeah.
yes.
So the title of my talk is Critical Exponents of Self-Worthing Box on n-simplex lattices. In fact, I would like to introduce first critical exponents, self-worthing box, n-simplex lattice. In geometry, a simplex is a generalization of the notion of a triangle or tetrahedron to arbitrary dimension in a given space. So this work is basically of Deepak work, and if he's in the audience, he may remember that probably it is his PhD work, which I am going to share on his completion of birthday. And I wish both of them, Deepak and Mustansir, many happy returns of their day. And I look forward for many fruitful contribution from them. So these are the examples of some of the simplexes, like 3 simplex, 4 simplex, 5, 6, 7, 8, 9. What is the idea that each vertex is connected with the rest of the vertices, and you go on connecting it like this. And the pattern will form like this. There's an analogous kind of thing which has been also introduced, Sierpinski gasket. This also falls on the similar class. The fractal dimension is given. Okay, how many number of simplex points you are getting. So if n is 3, then the fractal dimension is given as log 3 upon log 2. And the spectral dimension, this is defined as 2 log n upon log n plus 2. So now if you just keep these two values, if n goes to infinity, then the fractal dimension goes to infinity, while the spectral dimension will approach to 2. So this is the one of the characteristic of the n-simplex lattice or n-Sierpinski gasket. So second thing, we come to the self-worthing box. It is basically a path from one point to another, which never crosses itself. So this is the definition. Such paths are usually considered to occur on lattices, so that steps are only allowed in a discrete number of directions and of certain lengths. So these are the sum of the steps, like this is the 2-dimensional step walk. So these are the possible conformations. So by symmetry, you can take the other conformations also. So this is the 3-dimensional 3-step walk. This is 4-step walk. This is 5-step walk. So you can enumerate it, and then you can find out some of the statistics, whatever you wanted to know. For example, suppose you want to calculate what is the end-to-end distance of this walk. That you can calculate for all the individual walks and then average it, and then you try to find out. Or if you want to find out for a given step, how many number of conformations are there, that you can also calculate and study this. So if you take the self-worthing walk statistics, so the end-to-end distance scales as n to the power nu, where nu is certain exponent. The number of distinct conformation of n-step walk scales as mu to the power n, n to the power gamma minus 1, where mu is the connectivity constant of the lattice and gamma is some exponent. The number of closed polygons of n-step, which is also self-worthing walk, scales as mu to the power n, n to the power alpha minus 3. The beauty of this that long back in 1972, Jain established the relation for the spin magnetic system and source, and he shows that the correlation length T minus approach as T minus Tc to the power minus nu, the susceptibility goes as T minus Tc to the power minus gamma, and a specific hit goes as T minus Tc to the power minus alpha. The important that he established that these two belong to the same universality class. And in fact, when n goes to infinity, that corresponds to T minus Tc that approaches to 0. That is in the vicinity of the critical point. The exponent nu long back has been given by the formula by Flory, which says that it is 3 upon d plus 2 for self-Warding walk. This formula has been derived by the approximate by calculating the free energy of the attraction and excluded volume repulsion. But this formula has a remarkable success in the sense it gives the exact value in 1, 2, and 4 dimensions. But in 3 dimensions, it gives a very close value to the best known value of the exponents, whatever has been obtained either through the computation or some approximate solution. So motivated by this formula, there were a lot of attempts have been made to find out such kind of relations for fractal lattice or n-simplex lattices also. So this is the critical exponents. Then these are the solves self-Warding walk on n-simplex lattice. So I give some of the example. RF generation of a lattice over which a polymer enters and ends somewhere in this. Another partition function you can define that the polymer ends or self-Warding walk enters from one end and it comes out from outside, keeping this vertex remain untouched, so it doesn't visit that vertex. There may be another kind of possibility that box enters from one, it goes out and again come and enter like this and terminate here. And there is another possibility that both ends are in this segment, Rth order, and the polymers is somewhere outside. So given this, you can write down the partition function and you can establish a recursion relation between the Rh generation and R plus 1h generation. The same is true for the 4-simplex lattice. And again, the definitions remain the same, that polymer enters from one end and goes out from there. It goes from inside and come out from outside from the touching the two vertices. One end maybe one goes in and coming out and another comes in. So you can write down all the possible combination and you can write down the partition function. So if you go for 5-simplex lattice, so you can see that the complexity of the problem increases. So these are the sum of all the possible partition function, restricted partition function, I should say. And this is for the 6-simplex lattice. So the next task is to write down the recursion relation for all these n-simplex lattices. And particularly, I would request that this partition function, whenever polymer is going from in and coming out from, so like this is sufficient enough to calculate the value exponent nu using the renormalization. So let me just give you the brief concept that you write down AR plus 1, that is the R plus 1h generation in respect to the Rth fractal. So this is the Rth generation. So the polymer enters like this, or polymer may go like this, and which will give you the relation for this. So you are writing down the partition function for this, and these are the discrete partition functions which we are writing like this. So you can establish a recursion relation Br plus 1 is equal to Br square. So this is the Br square contribution. This is Br cube. This is the Br cube contribution. And then you can apply the renormalization group theory. So you iterate this equation for a given value of B, and you see either this equation will converge to 0 or it will diverge to infinity, but there will be non-trivial repulsive fixed point which will come at this. And if you solve this equation, the value of this fixed point comes something like 0.61803, and from there you can get the value of the connectivity constant also. This is the simplest way of approach to teach the graduate class also the renormalization group theory, because the students understand this very nicely. So to get the value of nu, just linearize this equation at the fixed point, and that gives the value 0.7986. If you remember in 2D Sierpinski gas, 2D, the value is 0.75. The fractal dimension of this lattice is 1.58. So if you increase this fractal dimension by increasing the value of B, one expects that the value will approach to 0.75. So this is the way I think work has been done in 1977 and 78 by Deepak, and it has more than 200 citations right now. So we have solved this model for 5 and 6 simplex lattice exactly, but then we said happen if you go for n-simplex lattice when n is very large. So in doing so what we realize that the fixed point A star, whatever we are writing this A star, that polymer is going from one end from the simplex and coming out from the other. So this goes as 1 by n. B star, when vertices are occupied, it goes as 1 by n square. C star is something like when all the vertices for 6 simplex lattice is occupied, then it goes as 1 by n2, and it can go like this. So if this is the condition, then we can, for simplicity, we can say that with the B star, C star term, we can neglect in the recursion relation and only incompare A star and on this equation. If you take this argument, then the recursion relation you can write is A square plus n minus 2n2. This is the exact equation you can write down. And for large n, you can approximate this with this equation. And if you linearize this equation and try to find out the fixed point, the fixed point is given like something A star 1 plus S upon 1 plus n, where the S value is like given like this. Using this value, you will differentiate this or linearize this equation with respect to the fixed point. The value of nu comes like the spectral dimension upon the fractal dimension 1 minus log n upon log n. So this is the formula, whatever is coming. So if you can see that if n goes to infinity, this term will go to 0, and this ds approaches to 2 while df approaches to infinity. It means the value of nu approaches to 0. This is something surprising, because in regular dimension, we always say that the nu value 4 is the upper critical dimension. So this doesn't happen to be true in case of n-simplex lattice. So with this work, which has been initiated by the Deepak.
So you have 1 more minute.
Yeah, so this work was initiated by Deepak in his early PhD days. But this model has been successfully applied to study the adsorption of polymer chain on fractal surfaces. Model can be solved exactly. While global transition of polymer on fractal lattices, this was also done by the Deepak and many groups, including our group at Banaras University. This is a new thing which we have predicted, that simultaneous adsorption and collapse transition of a polymer. And there we predicted a new phase, which is called surface attached global phase, which has been found later true in the Monte Carlo simulation or analytical theory, as well as in the experiments. And this has a lot of application in protein adsorption on the surface. Then we have developed 2 polymer chains on the fractal lattices, which interact with each other, and that we describe the DNA melting, so, and the multifractal behavior of n-simplex lattices. So these are the things which just initiated from the Deepak's early work, and I can very well say at this moment of time, I thought that just to remind Deepak that how much crucial importance he made in his early years, which is still fruitful and guiding to many of us. So thank you very much.
Thank you, sir, for such a wonderful talk. Any questions? You can raise your hands. Since we do not have any questions, so let's thank the Professor Sanjay Kumar. Thank you, sir.
Thank you very much.